The purpose of our experiment was to design an experiment to measure and calculate the coefficient of kinetic friction between two surfaces using real-world data and paper calculations. Our hypothesis was that the coefficient of kinetic friction between two surfaces can be found using measured mass, displacement, time of motion, and angle of an object's path. This will require kinematic equations as well as concepts of acceleration. The predicted coefficient of friction is somewhere between 0.25 and 0.75.
Plank! Cart! Wait. Stopwatch! Protractor.
We're doing another slow mo.
Meters. And scale. Scale.
The procedure went as follows. Place a mass in the cart and place on scale. Record total mass. Lean plank against the wall to create a ramp. Measure the base and height of the ramp. Use trigonometry or inverse tangent to solve for the inclined angle. Measure angle with protractor to verify result. Measure usable length of plank or the hypotenuse of the triangle. Place cart at the top of the plank and allow it to slide down. Measure the time using a stopwatch. Repeat 5 times to get an average time. Then, draw a free body diagram of forces shown in video. Solve for normal force and acceleration. Solve for coefficient of kinetic friction.
This experiment utilizes kinematic equations. The kinematic equations are needed using the variables of displacement, initial velocity, final velocity, time, and acceleration. Another aspect of the lab is knowledge of forces and acceleration. The force of gravity is mass times gravity, which is 9.8 times mass. The normal force is the reactionary force to the y component of the force of gravity. The force of kinematic friction, or Fk, can be found with the equation Fk equals mu k times Fn, which is the force of kinematic friction equals the coefficient of kinematic friction times the normal force. The force of gravity, if found on a ramp, has an x and a y component, which can be used using the angle and trigonometry. The x component of the force of gravity is Fg sine theta. The y component is Fg cosine theta. Incorporating acceleration, the sum of forces equals the mass times the acceleration, or F equals ma.
Plank against the wall. Vertically it was 0.62 meters, horizontal it was 1 meters. We used inverse tangent to find the angle of 0.62 over 1 and got the angle of 31.799 degrees. We verified it with the protractor and we measured out the plank to be 1.1 meters, or 1.15.
Film for Obama.
That should be
1.3. As soon as you can see that explosion.
You're good. Where did you mark it?
1.3.
Hold it and type. I already got someone tying something.
1.29.
Yeah. Take off that tape. Alright, what's the new mass of this going to be?
1.2.
Did you change it?
Alright.
For each trial, we let the car slide down the ramp. Trial 1, the time was 1.3 seconds. Trial 2, the time was 1.3 seconds. Trial 3 was 1.29 seconds. Trial 4 was 1.2 seconds. Trial 5 was 1.2 seconds.
body diagram for the experiment. As you can see, there are three forces acting on the cart as it slides down the ramp. We have the force of gravity, which is pulling the cart down the ramp. We have the force of friction, which is restricting the movement of the cart down the ramp. And we have the normal force, which is keeping the cart on the ramp, making sure it doesn't fall through the ramp. So we have four forces technically though, because we have the x and y piece of gravity, which you can solve for by using your angle with the cosine and sine.
Since the cart in the y direction is not accelerating, it's staying on the board, therefore the acceleration on times a is going to be 0. So summing the forces in the y direction, we have the normal force minus the force of gravity on the ramp is going to equal 0. So you use this to find plugging in the angles and the values to find your normal force of 1.92, which is
Go.
In the x-axis case, there is acceleration, so you have to use F equals ma to figure out the forces and the acceleration. So, you use Fg sine theta for the gravitational force on the x-axis, minus the force of friction is going to equal the acceleration times mass, like F equals ma. Plugging in all the numbers, you are now down to this equation.
Go.
Now we need to solve for acceleration.
This is a kinematics thing. Well, length, and then we put the 1/2 a t squared. Then we solve for a. And then boom.
Action.
So we plug in a. We just got a page from UK. UK.
Are you sure?
The coefficient of kinetic friction is 0.446.
Analysis. This experiment has datatrons and possible observations. The recorded times were consistent, contributing verification to the lab design. The system was acted on by three forces: force of gravity, normal force, and force of friction. The x and y components of the force of gravity act as action forces, while the normal force and the force of friction are reaction forces. When the forces are summed up in the y direction, it can be set equal to 0 because the system will be in equilibrium. When the forces are summed up in the x direction, it can be plugged into the equation F equals ma because the system has horizontal movement. This incorporates kinematics to the idea of forces. Conclusion. In the end, the lab was successful in calculating the coefficient of kinetic friction using kinematics and forces. The experiment allowed us to see how the coefficient of friction affects friction and how it can be found from other properties of physics. Using kinematics and dynamic equations, we were able to calculate the coefficient. The hypothesis was indeed validated, as the coefficient turned out to be in the original predicted range of 0.25 to 0.75. The understanding of physics as a whole was strengthened as a group because of the ability to visualize and see what was happening instead of looking at printed pictures and numbers. The real-world scenario allowed us to calculate these numbers using various methods. The experiment could be further extended to verify the coefficient using different incline angles and maybe even a whole new approach, not using ramps but instead lines and weights.
There are many possible errors that could have occurred within this experiment, 3 of which are mechanical error that could have occurred with the scale to measure mass, the stopwatch to measure time, and the meter stick to measure lengths. Measurement errors could also be an aspect of the lab, with the measurement of time and length. Some possible improvements to decrease this error can be using a cart with exact mass, using more careful measurements, and using a more advanced tool to measure time more precisely.